we're looking at chapter 4. This is section 1. We're going to be building on our parent graphs. You have a head start because we've already talked about the parent graph y equals x squared. Remember transformational form? And we're looking at absolute values, quadratic, cubic, square root, cube root, etc. This is the day for just quadratics. When you're in this form, what's the vertical stretch factor? A. The vertical stretch factor is A. The horizontal stretch factor is going to be, what is the horizontal stretch factor? What is it? 1 over B. And remember that it has to be in the form of B times the quantity x minus c. It has to be in a factored form, B times the quantity x minus c. And where we move the origin, the translation vector is going to be not negative c, c comma d. It's the opposite of what's with the x. So in this case, you would say, okay, I have a minus c. So the opposite of that would be a positive c, or whatever c is. Remember, these are variables. So whatever's with the x, take the opposite. That's the general rule. Yeah.
For the quadratic, it's...
Right now we're just here. Bear with me. We're not talking, we're right here. General form. We're not talking about a quadratic. We're just right here.
Okay.
We're just reviewing. Okay? Everybody good with A, 1 over B, and C, D? You guys have already demonstrated you're pretty good at that. The 2 or 3 of you who aren't using this, now's the time to get on the boat. Because those 2 or 3 people all made errors when they weren't using this way to graph. It's time to get on board. So now you're looking at a quadratic function, standard form, looks like this, ax squared plus bx plus c. That is not transformational form. Okay? This is not transformational form. This is called standard form for a quadratic. Remember, the way you can tell you're dealing with the quadratic, if you multiplied everything out, got rid of all your parentheses, and the highest power on your variable is a 2, then you have what we call a quadratic function. This one happens to be presented to you in standard form. And every time you graph a quadratic, what are you going to get?
X percent.
Every time you're going to get a parabola. So when you graph any quadratic function where a is not a 0, you're going to get a graph that's going to be parabolic shaped. Doesn't really matter where that parabola is. You get a parabola-shaped function. This is our parent graph. Rarely do we put the 1. We're just throwing the 1 there and here. This is more likely what you're going to see, y equals x squared. That's your parent graph. You already know this graph, correct? Starting at the origin, how do we get to our first point? Right 1 up 1. Right 2. And if you wanted to, you could go right 3 up 9. Left 1, left 2, up 4, and left 3, up 9. Now, we were talking about this specific chapter in the honors class, honors pre-calc class today, or yesterday, excuse me. We, in chapter 4, beat quadratics to death. So some of you have some experience with quadratics. You're going to have a lot of experience with quadratics by the time we finish this chapter. This is our parent graph. The add-on to this is the axis of symmetry. You're going to need to start being able to identify it, and you're going to have to be able to identify it by an equation and on the graph. On the graph, we're going to use a highlighter, and it will be dotted. The dotted line indicates that these points on this red dotted line are not really part of the graph. They're just there as an assistance to the graph. And what we're looking at is mirror images through the axis of symmetry. And there are other places in mathematics where we have lines that act as lines of symmetry. Parabolas are ones where we start saying, okay, let's identify what it is, and let's see if you can identify the equation. So these are the critical movements. We've had these before, so I don't anticipate that being very difficult for you. Again, these notes will be posted online before I leave today. This is standard form. Now, some of you remember this, some of you don't. When you're in standard form, if you want to find the vertex, we use the opposite of b over 2 times a to find that vertex. That opposite of b over 2a comes back a little bit later in this chapter, and we'll hopefully someone will say, hey, isn't that? And we'll have this conversation in a week or so. Once you know what the x coordinate of the vertex is, the opposite of b over 2a, if you know the x, plug it in for x into your equation, you'll find y. Look,
Thank you.
you can watch this weekend.
Okay.
That'll be fun, huh? All right, so once you know what the x is, plug it in and you'll get the y value. A is still going to be your vertical stretch factor, even in standard form. So the leading coefficient on the x squared is still the vertical stretch factor. And we still multiply the ups of our parent graph with whatever A is. When A is positive, you get a horseshoe up. It's important that you realize this vertex is called a minimum. You know, I once had a kid in Algebra 2. This has got to be 23 years ago, 24 years ago. I had this kid. I can't remember his last name, but I remember his first name. I remember how he looked vividly. He was one of my most brilliant kids, certainly the top 2 or 3. And he is one of the only 2 or 3 kids that I have ever had that had a photographic memory. And he would look at this page, and his eyes were like a camera. Once he blinked, it was like, boom, on the hard drive. He didn't have to study because everything was right there at his fingertips. It was amazing to watch this kid. He was brilliant, just absolutely brilliant. I had him, I think he was a freshman taking Algebra 2, and that was back in the day when this room was only filled with juniors. A couple of seniors only, but Algebra 2 is a junior level course. Those of you sitting here watching and you're not taking notes, I hope you're as good as that kid is, because he never missed a point in the class. And if you're not taking notes, you need to start learning to be a better student. If your A value is less than 0, you're going to have a horseshoe down, and the vertex will be called a maximum. And those two things are very important to be able to identify the min or the max just by looking at the equation. Now, if I just go back to the graph here for a second, take a look at our axis of symmetry, this red dotted line. How would you describe that line? No, yeah, that's an equation, but that's not describing the line. It's vertical. This is a vertical line. And vertical lines all have an equation that sounds like, in this case, 0, but in general, it's going to be x equals. So remember, when we get down to the axis of symmetry, your equation is a linear equation. You're not finding the value for x that solves something. This is a linear equation. X equals the opposite of b over 2a. It's going to be whatever the x coordinate of our vertex is. Okay? Whatever the x coordinate of the vertex is, that's what we're looking for. Because the axis of symmetry will always go directly through the vertex. Remember, this is the equation of a vertical line. Probably 9 out of 10 people who get the axis of symmetry wrong on the test or a quiz tell me the axis of symmetry is 6. The axis of symmetry is -4. And I'll write x equals 6. X equals -4. It's got to be written as a linear equation. Now, standard form again, if you're in standard form, always the value of c will be the y-coordinate of the y-intercept. Your y-intercept will be 0, c. Did I go too fast?
No, it's just a very
What?
It's just a very right?
Yes, what did I say?
Misspelled. Very cow.
Sorry about that. Everybody good there? Here is the graph of our parent graph, which we've already spent a fair bit of time with. And right 1, here's your up 1. Right 2, here's your up 2. And right 3, here's your up, sorry. Right 2, up 4. And your right 3, up 9. Right? Take a look at all of these equations. Okay, they are all quadratics. Therefore, their graphs are all parabolas. What do all of these have in common? They all have just a vertical stretch factor, which means the origin 0, 0 is where the vertex will be for all of them. Okay, these only have a vertical stretch factor. So when we look at the graphs, there's y equals -x squared. What's the vertical stretch on that? -1. So compared to our parent graphs, right 1 up 1 becomes right 1 down 1. Right 2 up 4 was right 2. So what gets impacted when we look at our parent graph for this example? So what got impacted on our parent graph? The ups. Just the ups. What do you expect this graph to do to the parent graph? Twice as tall. So when we connect here, instead of right 1 up 1, we go right 1 up 2. Instead of up 4, it's up 8. Instead of up 9, it's up 18. What do you expect on this third one? Same thing, upside down. So it is going to be twice as tall, but it's flipped now. Now this is posing problems for people. Okay, there's still a good chunk of people, 3, 4, 5, 6 of you, are calling this a horizontal stretch factor because it's a fraction. Just because it's a fraction doesn't make you do that. Where is it? It's in front of the x squared, so this 1/2 is still a vertical stretch factor. What do you expect to happen to the parent graph?
Twice as wide.
No. Half as tall. So when we graph this, instead of going up 1, 4, and 9, you're going to go up 1/2, 2, and 4 1/2. So it took the parent graph and squished it in half, vertically. Now it does make it wider, but as soon as you are thinking wide because of this 1/2, you've missed the whole deal. This is a vertical stretch factor. So it's half as tall. This one's going to be half as tall and flipped. So it's flatter and then upside down because of the negative. What's the 3 going to do down here? 3 times as tall? Yeah, 3 times taller. So this one is going to be pretty skinny compared to the parent graph. So you're up 3, you're up 12, and you're already off the page. Oh, you're not off the page, but on the third you're off the page. Okay, you're not. Julia. Where's Julia? Where are you going? For real? Yeah. It's Friday, 3-day weekend, you're heading up to tower early. All right, is everybody good here? What does the vertical stretch factor affect in our parent graph? The ups. And the vertical stretch factor affects the ups. It affects the y components of our graph. Now, some of you, almost all of you, did a great job making your list for the test that we just took. You need to make sure you continue that. Parent graph, translation vector, vertical stretch. If there's a horizontal stretch, include that. Axis of symmetry, add to this when we're doing the quadratics. And then ultimately they're going to ask you for the x-intercepts and sometimes even the y-intercept. Okay? Right now we're just looking at doing that from a graphic standpoint of view. If we graph it, we can also put the parent graph on there, you can see it. Whoops. So you can see the parent graph here in red, and then the purple will show the graph that we have here. If you make your list, your parent graph is going to be y equals x squared. What's your translation vector? 0, 0. 0, 0. We have no movement whatsoever on that. And then the vertical stretch we said was a half. Here's where we've got to be really careful. What is the axis of symmetry? X equals 0. How do you know? It's always going to be whatever the x coordinate of your vertex is, or your translation vector component. X equals whatever this is. And that makes it a vertical line. And then the x-intercept, that's easy in this particular one. So what will we say? And that's as an ordered pair. Sometimes there will be 2 x-intercepts. Sometimes there will be none. If they're asking for x-intercepts and there aren't any, just say so. There's no x-intercept. Nothing wrong with that. Okay? What's the parent graph? X squared. Translating this time will be 0, 0. Vertical stretch. And the axis of symmetry is x equals 0. X-intercept? 0. Make sure you write them as ordered pairs. Yes, sir.
Is the translation vector pretty much the same thing as x-intercept?
No.
What's the difference?
The difference is that it's a coincidence that they're the same net.
Oh,
So
okay.
if you sit tight, we're doing these only with stretching right now.
Uh-huh.
So when you look at our graph, you know, and we say, okay, we're going to be at the origin, and then it's going to go right 1. Where are we going from right 1?
1.
No. Take a look.
Oh, up 3.
Up 3. Left 1 up. Whoops. Left 1 up 3. And then right 2, you're going to end up going up
12.
12. So we're going to be way up here. Left 2, way up here at 12. So we won't have.
So the last point, so 3, so
if you look at where does the graph cross the x-axis, it's at 0, 0.
Oh, okay.
Okay, that's what we mean by the x-intercept. And then when we throw the axis of symmetry in there, it's going to look like that. Dotted, highlighted line. Okay? You need to use a highlighter. This is not going to, we are not going to keep having negotiations on this. Alright. So negative 2x squared, what do you expect to happen on this one? Twice as long, or twice as tall, and upside down. Okay? So your parent graph is still y equals x squared. We're still at 0, 0, and we're still looking at a vertical stretch only on this. So x equals 0, 0, 0 again. So when we look at this graph, we start at the origin, and then it's going to be right 1, down 2. So left 1, down 2. And right 2, down. Everybody okay with the vertical stretching? Yes. Yeah. So now, let's see what happens when we do something besides just a vertical stretching. Remember, because you're not in transformational form, you've got to be very careful on how you treat this type of a problem. For me, I visualize that as being in transformational form. Other people visualize this as being in standard form. In standard form, if you think about it like this, you'd have to have the b term in there also. You'd have to say y equals negative 2x squared plus how many x's? 0 plus 4. So that's A, B, and C. But because there's no b value, there is no bx term in this standard form, I tend to want to say, let's think about it like this. Because transformational form for me is just so much easier. And I'm fine with you doing it either way. I'm also fine with you recognizing when b is not there, like in this example, if you just have an ax squared plus c, then your parent graph, it will be the y equals x squared. Your translation vector will always be 0, comma c. Always. If you're in that form. And your vertical stretch factor is negative 2. Your axis of symmetry is x equals 0. And then your x-intercepts, we're going to have to see what happens when we graph it. So we're going to start now at 0, 4. And you're going to go right 1, down 2. And left 1, down 2. Right 2, down 8. And left 2, down 8. So when you graph this time, you can see that the x-intercepts end up here and here. You also should be able to see that you can't tell what they are. Okay, in terms of the exact value. We can figure it out. It's not very hard to figure out. But they're square roots, square root of 2. So it's like 1.414. But it's not important for you to know that right at this moment. Just that that's where the x-intercepts are.
Actually, should they be halfway between, oh no, I see.
But now I just want us to like how they
Don't even worry about them right now. Unless they say, what are they, then just give me a ballpark. If you said 1.5 for those, I could live with it. Anything in that ballpark. Between 1 and 2 would be fine.
between negative 1 and negative 2.
We care only when we can tell you what they are specifically. Okay? So now you can see what's happened with the parent graph. parent graph, the parent graph was raised up 4 units, flipped over, and stretched by a factor of 2. But it's the same exact shape as that parent graph. Your x-intercepts, we aren't going to be able to find that right now. And your axis of symmetry is still going to go x equals 0, the x coordinate of your vertex. Everybody with me so far? So anytime you're in this form, your vertex is going to be 0, c. 0, comma, negative 2. Yes, it is. So your parent graph is y equals x squared. Your vertical stretch factor is a half. And your axis of symmetry is x equals 0. So we're going to start at 0, negative 2. But instead of going right 1, up 1, what are you going to do?
Right 1, down, up,
Yeah? Right 1, up a half. Right 2, up 2. Left 1, up a half. Left 2, up 2. Right 3, up 4 and a half. If you wanted to, you could go to right 4, up. Pretty good. So the parent graph got moved down 2 units and then squished as well by a factor of that. Any questions there? So now we're back to standard form all the way. All right, this is a very common form that you get equations in, x squared minus 2x minus 8. The equation of a launched object is going to look like that, for example. We have all types of applications for this. You've got to be able to graph it nonetheless. The key is recognizing, hey, I'm in standard form, so I can say my parent graph is still y equals x squared, but my translation vector is going to be a whole lot harder to find. How about the vertical stretch factor? In this case, it's 1, because it's always going to be whatever a is. In order to find the translation vector, the x coordinate of our vertex is the opposite of b over 2 times a. Those of you wearing your t-shirt, this t-shirt, what's this stand for? Seriously? We're not handing out loser t-shirts here. What's this stand for? Large? Could be, but it isn't large. I mean, you're a big guy, but I don't think I'm giving you a t-shirt that says you're that big. In this class, you all have it. I'm the king of it. No, I am Lockeray, yes, but that's not what the L stands for. You all have it. You all are this. Yes. Okay, you're all looking to cut shortcuts and not show work. You can't do it. So stop doing. If it says this, then no matter what B and A are, it's going to be a minus here, then a fraction. And then it's going to be B, negative 2, over 2 times A, which is 1. Please do not change that to a positive 2 because this negative and this negative cancel when you're doing your work. In the next step, absolutely. Wait, what?
Where do you get that negative? Where do you get that?
Do you have notes?
Negative.
Look in your notes. It's right there.
Negative.
This is the formula. We're just plugging into the formula. The opposite of negative 2 divided by 2 is going to give you 1. So the x coordinate of our vertex is going to be 1. That means our translation vector is 1 comma something. And the axis of symmetry will be So when you do the opposite of b over 2a, you have a lot of information you just found.
I know there's not a horizontal stretch factor.
Because I'm in standard form, and there's never a horizontal stretch factor in standard form.
Oh, okay.
So now, how do I find out what the y component of my vertex is?
Plug it in.
Plug it in. Now, some of you are going to pull out your t-shirt and say, Mr. Lockray, you know what I can do to find this? I can do this in my head. When you take this class again next fall, don't do that. Okay? Write it down. Y is equal to 1 squared minus 2 times 1 minus 8. And again, I'm not trying to convince you that you can't do it in your head, but if you don't do it like this every time, when you need to do it, and you're only working in your head, you're going to screw it up. 1 minus 2 minus 8. Negative 9. Very good. So 1 negative 9.
No, that's negative 7. Oh, no, negative 9.
We might want to put a sensor on.
No,
I know, but you're a blurter. You're a blurter. I'm just trying to help you out. You're a blurter. When you're going to blur it, just put that screen up that says, okay, check it again before I blur it.
Okay, I'll stop.
Because you're going really fast and you're doing it in your head. So let's look at what the graph should look like. 1 negative 9 is way the heck down here. From that point, what do you expect to see? Parent graph. Right 1, up 1, right 2, and right 3, up 9. Left 1, 1, left 2, up 4, and left 3, up 9. So you can see on this one that the intercepts, the x-intercepts are integral, easy to identify, negative 2, 0, and 4, 0. Now, be careful with that, okay? It's not negative 2 and 4. Got to write them as ordered pairs. Got to look just like this. What am I missing in my picture? Axis of symmetry. So just bust out your ruler with a highlighter and right through your vertex, draw a dotted, highlighted line. Everybody good with that? Standard form, not necessarily my favorite. But you've got to be able to work with it. See if you can do this one right here. Threw a little bit extra in this part. All right, here we go. Again, way too many careless mistakes. You cannot put the t-shirt on. You have to work things out meticulously. Every single time in your life that you try to take a shortcut, not every time, if you try to take these shortcuts, you're going to end up doing twice as much work to make up for the fact that you screwed up on the shortcut. There aren't really a lot of shortcuts in the world. So don't look for them here. When we're doing this problem, and I need to find the translation vector, all right? X is going to equal the opposite of 6 over 2 times negative 1. There's two negatives here. They cancel. 6 divided by 2 is going to give me a 3 for the x coordinate of my vertex. I did it in my head is not what you want to do because, again, simple problem. Oh, I can do it in my head. And when you do that, that's when you make the mistakes. Y equals negative 3 squared plus 6 times 3 minus 8. Every time you substitute in for x, every single time, put parentheses around what you're substituting. And you're less likely to make dumb mistakes. 3 squared is 9. This is negative 9. Plus 18 minus 8. That's going to give you a y value of 1 in the translation. Now, it's not a touchdown dance here. You're just making the list. Don't forget, in your list, vertical stretch is -1, and the axis of symmetry is x equals 3. Does anybody have a question on the list? If I don't see the list, no partial credit. Okay, and there's a few of you who found that out on the test. Make the list. 3-1. From there, right 1, down 1. And then we get 2 nice pretty x-intercepts. And let's go right 2, down 4. Is that right? Up 2, down 4. If we connect those up, there's our graph. Easy to see the x-intercepts now. What are they? 0, other way. 2, 0, 4, 0. Remember, it's x comma y, and y is the 0 part. Axis of symmetry, should throw that in there too. Should look like that. Have fun now. Everybody good here? Okay. Let's do one more just for fun. We'll do it together. What's the parent graph at this point? Okay. Again, I know you think you can do this all in your head, and it's not wrong to do that. I'm just telling you, you are going to make careless mistakes. And if out of 20 problems you make a careless mistake one time, that's too many. You can't risk that when all you are talking about doing is the opposite of 6 over 2 times 2. Show your work. So you're going to get the opposite of 6 over 4, or -3/2. The x-coordinate of your vertex, your translation component, your x component is -3/2. Does everybody follow that? When you get fractional translations, that makes things a little bit more challenging, especially on the plug in. So when we plug in a -3/2, you're going to have y equals 2 times -3 over 2 squared plus 6 times -3 over 2 plus 3. You want to be the best. You want to be the elite. You want to be the star in the room. Don't use your calculator. Learn how to work with fractions. More than 50% of the people in the room struggle with this problem without a calculator. It's not difficult, they just struggle because they don't work with fractions. When you square this, you're going to get 9 over 4. When you multiply, you're going to get -18 over 2 plus 3. When we reduce right here, you're going to get 9 over 2 -18 over 2 plus 6 over 2. I'm just putting the 3 to a 6 over 2 for a common denominator. So a -9 and a +6 is a -3 over 2. How coincidental. Same as the x. And that's all it is a coincidence. What's the vertical stretch? What's the axis of symmetry? As an equation? And we don't know what's going to happen with these x-intercepts. But if you follow the rule, graphing is still easy. -3 over 2, -3 over 2. There's your vertex. From there, what do we do? Right left one up 2 also. Right 2, left 2 up 8. So when we graph that, graph looks just like that. Your axis of symmetry. What'd you forget? Okay, and then we don't have to worry about the x-intercepts at this point because they're not going to be nice, pretty points. Any questions on graphing from standard?
So you could say x-intercept 1 is...
No, we're going to not worry about the x-intercepts because they're not integral.
Okay.
Don't worry about it. Not a big deal at all right now. The x-intercepts are a big deal in this chapter, but I don't want a ballpark x-intercept. Okay? I don't want a doctor who knows some of the organs inside of my body. Okay, and we open it up and we say, well, I think it's this. It's close to here. That's not what we want. So right now, if it's not exact, don't worry about it. That's it. Yeah, if it's not exact, we don't need to ballpark it at all. Let me go back to these examples and let me ask you a couple questions. So in this example, what's this point called? Tell me something else. It's the minimum. Okay? The lowest value for y that you can get here. You have all these y values and all these points. The smallest y you can get is this one, which is 0. That's the minimum value. What's this one called? Maximum. The purple one? That's got a maximum. What's the maximum value for the function? 0. But what's the maximum value for the function? Someone said it. It's not 0. It's 4. The biggest y value you can get is 4. There's no other points above the 4 on this purple graph. What domain or x value will give you the maximum? 0. What's this graph? What's the point right here? But what is it called? Minimum. And the minimum value is -2. What's this graph? This point is a minimum. What's the smallest value for the function? -9. What x value, what domain value gives you that? 1. 1, -9. When x is 1, you get the smallest y you can get on that graph. Minimums and maximums. When a is positive, your vertex is a minimum. When a is negative, your vertex is a maximum. It's that simple. It's that simple. And you want to always have that right in the front of your brain when you're going through this stuff. And you graph. If your graph is a horseshoe up and vertical stretch is negative, oops. So this kind of a question is a two-part question. Okay? Half of you are going to answer the second question wrong right now when you do this. But I want to know, just write down whether this function is a max or a min. Write it down. And then find the maximum or minimum value. So is it a maximum or minimum? Write it down. So we said it's a maximum. What was the maximum value?
5.
The maximum value is not 1, 5. It's just 5. You are looking for the maximum or minimum value. You're looking for what the y is on the vertex. So x turned out to be 1, and y turned out to be 5. If you don't see that, and I haven't written anything down, just stick your hand up so we know that you didn't get it. If you don't put your hand up, the only one you're hurting is you. So everybody got 1, 5, and the value that we want is 5. But let me tell you again, if you're not doing it, or you didn't get it, and you're not asking to see it, you're making a huge mistake. Okay? Does the function have a maximum or minimum? It has a maximum. Can anyone tell me what it is? Excellent. It's 3. Remember, when there's no bx term, your vertex is 0, C. 0, 3. So this has a maximum value of 3, and it's, so we're looking at a horseshoe down. The last one I want to show you is when you're setting up some of these application problems. You have given information, and they want you to write a function that models, in this case, revenue from bike sales. You sell 50 mountain bikes a month, $2.20 each, and for each $20 decrease in price, you'll sell 10 more bikes per month. This problem is really confusing the way they word it, but they can't word it any better. You own the bike shop, and these are your sales. But you got an accountant that says, you know, look, if you drop your price for like $20, you're going to sell 10 more bikes. More bikes, more revenue. Now, eventually, you could give the bikes away. You'd get rid of a lot of them, but you're going to go out of business. Okay, yeah, you're not going to make anything. So what we want to do is we want to let x equal the number of $20 decreases that we do. So the cost of a bike is going to equal how much? 220 minus, not x, x times 20, or 20x. We don't need parentheses. So if x is 0, if we decide, no, I'm leaving my price alone, then the cost will stay 220. If we drop it one time, it's 220 minus 20 is 200. 2 drops would be 180. 3 drops, 160. How about the number of bikes? Number sold. 50 plus 10x. Excellent job. How do you find revenue for this example?
220 times
Cost times number sold. Revenue equals cost times number sold. Here's your cost. And here is your number sold. And if you multiply those together, you're going to get your function in standard form. The question is going to ask you what price produces the maximum revenue. Okay, what price produces the maximum revenue? Where are you going to find the maximum revenue?
Y.
Somebody said it. The vertex, very good. Is it, do we need to know the x or the y? We need to know the x. It doesn't say what is the revenue. It says what price. So we got to figure out what x is, and then go back up to the cost. If x is 3, you plug in a 3. If x is 8, plug in an 8. Okay. But in order to find that maximum revenue for you guys right now, you would want to turn that into standard form. If I asked you how to find, what would the x-intercepts be? We would do 0 equals 220 minus 20x and 50 plus 10x. We can kind of cheat the system here. How do I find the x-intercepts? If the y is 0, how do I solve this? You could, but you'd have to multiply that all out, and we haven't really talked about that, but this is back to Algebra 1. Something times something equals 0. Make them each equal to 0. And then solve. So 220 equals 20x, and you're going to get 11 equals x. Over here, 50 plus 10x equals 0. And you're going to get negative 5. Where is halfway between these two? What's halfway between 11 and negative 5? Here's negative 5, here's 11. Because our graph's going to look like this. Halfway between, add them up, and divide by 2. 3. So halfway is going to be x equals 3. That means the vertex is 3 comma something. That means x is 3. What price should you sell your bikes for? If x is 3, what should we sell them for? $160. That problem is a tough problem, especially at the last part of a Friday. Got it? This is your assignment. I want to give you a new calendar because our calendar is off. I have not posted it online. As soon as I have the new format, which we're working on right now, I will post these online.